now we can start. Okay, so I want to suggest that there are two basic approaches to defining useful mathematical frameworks, general mathematical frameworks in which one can study probabilistic theories ranging from classical probability theory to quantum probability theory, and perhaps considering other things as well. And these two approaches are, roughly speaking, a top-down approach, very well represented in this audience, in which one starts with the assumption that whatever else it might be, a theory of the type we're interested in, should be represented by some sort of a category, and in order to accommodate the possibility of, so to speak, composing systems in parallel, this category should come equipped with something like a tensor product, some sort of monoidal product, presumably symmetric. At any rate, that's the usual setting. Some sort of symmetric monoidal category is the starting point, and then one proceeds to add further structural features, perhaps, or additional constraints, and look at the consequences of those. One might require the category to be closed, or to be compact closed, or what have you. The other approach, actually an older approach, I tend to think of it as going back to Mackey's work in the late 50s, is to construct probabilistic models, let's call them, being a little bit vague, to construct probabilistic models by hand, to say exactly what sort of a structure you mean by a probabilistic model, and to come up with examples, and then to try to come up in an equally constructive vein with constructions that let you compose these in various ways, and to build up one's theory in this way. Now, we would like these two approaches to articulate well. You'd sort of like the constructive bottom-up approach to produce categories that at the end of the day are very nice as symmetric monoidal categories, since ultimately one's goal is to try to understand quantum probability and things like it. And conversely, it may be that the top-down approach gives you some constraints on the model. Okay, so So here's a problem about that articulation. This bottom-up approach, which I'm going to describe in a good deal more detail in just a moment, or at least I'll describe one version of it in detail. This bottom-up approach leads pretty naturally to categories of, well, I guess we can still call probabilistic models, but these categories are not usually monoidal. In fact, they usually have two tensor products, at least. There's a kind of maximal tensor product, which allows for entangled states between separated systems, but doesn't allow for any entangled measurements. And there's a minimal tensor product that allows for no entangled states at all states in that product are separable, but it allows for lots of entangled measurements. So, okay, that's still interesting, and one can do actually a lot with that, but if our goal is to account for the structure of quantum mechanics, then we'd like to have a single monoidal tensor product, a sort of canonical tensor product that's somehow in between these two, and that allows for both kinds of entanglement. That's what we'd like to get. But since the existence of such a single preferred canonical both state and measurement entanglement tensor product is one of the things about quantum mechanics that you would presumably like to explain, one would like, at least ideally, not to have to just postulate that. One would actually like to see that emerge from some construction. You'd like to know what that tensor product is, maybe from an operational point. Okay, what I'm going to do in this talk is to try to, I say here show, but perhaps better I should say, I'll try to persuade you that if we insist that our construction of probabilistic models, on the one hand, be very uniform, be done in a sort of consistent, uniform way, I'll specify what I mean by that, And if we also insist that the models that we are building in this uniform way all be very highly symmetric in a way that I'll also specify, then those two requirements actually do lead to at least a natural candidate for a single preferred tensor product. I'll also show you some examples, however, that show that this single preferred tensor product can be somewhat ill-behaved, or depending on your point of view, maybe somewhat interesting. However, if we impose a couple of additional constraints that I think are fairly natural, this product will turn out to be symmetric monoidal, a symmetric monoidal bifunctorial product on a suitable category of models. And it will also have a non-signaling feature, which is attractive, and probably is heterometer in such a product. Okay, here's a quick outline of the talk. Prakash, from when am I starting my talk? 11:29. Okay, good. So I'm going to quickly start with an overview of the kind of object that I'm going to take as representative of a probabilistic model. Something called a test space. Some of you have heard me talk about these before, but others haven't. I'll talk about how you form composites of test spaces in a sense that doesn't specify yet a unique such composite. Then I'll talk about what I mean by a very symmetric test space, the kind of model that I'd like to build. And then I'll talk about how you go from the practice of building individual highly symmetric test spaces on a sort of ad hoc basis to a scheme for building a whole bunch of them all at once, a whole theory's worth, in a uniform way. And it's that then leads to what I think are perhaps some interesting results. Okay, so jumping in then. A test space is just a collection, I'll call it generically Fraktur A, of non-empty sets, which I'll call tests. I want you to understand that each set in this collection, each test in this collection, is the outcome set of some measurement that you can make. So that's all it is. It's just a collection of outcome sets of measurements. And for purposes of this talk, let's assume finite measurements with finite outcomes, though ultimately I don't really need that restriction. Okay, so that's a little bit. If I have a test space Fraktur A, I might want to take all of the outcomes of all of the tests and put them in one big bag. That's, of course, taking the union of the set of tests. I'll generically call that union capital X, and I'll refer to that as the outcome space, or the test space. All right, once I have that much structure, I can now define what I mean by a probability weight, or as I'm also going to call it, a state on Fraktur A. It's just a mapping, let's call it little alpha, that assigns to every outcome of every experiment.
It's 12:30.
Thank you. A real number would be 31. It's not even quite 11:30. No, so a state should assign to every outcome a value between 0 and 1, a real number between 0 and 1. And those values, which I intend to interpret as probabilities of securing various outcomes, those probabilities should sum to 1, certainly not over the whole outcome space, but rather just over the outcomes constituting a particular test. And that should be the case for every test. So this is a sort of non-contextual assignment of probability symmetric outcomes. I want to mention that because, notice, I do not say in the definition of a test space that it's a collection of pairwise disjoint sets. I'm allowing for the possibility that two different experiments may have some outcomes in common. Oh yes, thank you. Turn off the voice. Good. Okay, but not mine. Good. Thank you. Okay. All right. Good. I'm not going to need this very much, but just briefly to refer to it. If you take the collection of all states or probability weights in the test space, that is, of course, a convex set of functions on X. Call it capital omega of the test space. I'll call that the state space of the test space, and the span of that convex set ordered pointwise I'll call V of omega, subject to some reasonable conditions. That set will be compact, and you get a nice base norm space and so on. So that sort of ordered vector spaces framework for generalized probability theory emerges naturally within this framework. In fact, you can think of this as kind of a concrete representation for such a thing. Okay, let me give you a couple of quick examples. The simplest one is a classical test space. There's only one measurement. So Fraktur A is the singleton whose only member is the single outcome set E. In this case, states, probability weights that is, are simply probability weights in the usual sense on that set. Pure states, if we want to look at extreme points in the state space, are point masses, and every state's uniquely a mixture of pure states, so the state space is a simplex. Not a fact that I'll actually use here, but just worth mentioning. The other benchmark example is this. If H is a Hilbert space, let's say for present purposes finite dimensional and complex, then consider the collection Fraktur F of H that consists of all the unordered orthonormal bases for H, what are sometimes called frames of H, hence F of H. Gleason's theorem tells us that states on that test space, in fact Gleason's theorem as originally formulated says exactly states on that test space are uniquely represented by density operators. W a density operator rho, so that's a type of thing. Rho a density operator rho on H. So we get the usual framework of at least elementary quantum mechanics pretty naturally this way too. Okay, now I want to show you two further examples just for reference. In both of these examples, I want to start with a finite set E, fixed finite set E, sort of a basic experiment that we start with maybe for reference. My first slightly funny example is this. Let Fraktur Gur of E, maybe, denote the grid test space, by which I simply mean the set of rows and columns of the Cartesian product E cross E, regarded as a rectangular E-indexed array. Okay? So it's a big Cartesian product, think of it as an array. The rows are subsets thereof, the columns are subsets thereof. Take those sets and just declare those to be your tests. It's pretty clear that then states would be functions on E cross E, that would be the total outcome space, that add up to 1 independently on every row and every column. So that's a doubly stochastic E by E matrix. The state space is a nice, well-studied convex set. The extreme points would be permutation matrices. The states, therefore, convex combinations of that sort of matrix. Okay? So far, so good? That's a test space. Nice state space. Here's another slightly more interesting example. I'm going to let Fraktur B of E be the set of graphs of permutations of E. A set of graphs of permutations of E. Precisely the sets whose characteristic functions would be the permutation matrices that were the extreme points in the state space in the previous example. If F is such a permutation, a bijection from E to E, let gamma sub F be its graph. States on this collection of graphs of bijections again can be regarded as E by E matrices, but this time they're convex combinations, as it turns out, either of row states, where a row state is a state that assigns to an ordered pair UV 1 if U equals X, so 1 if you're in the X row and 0 otherwise, and a column state's defined dual. Okay? So there's a sense in which these two examples are dual to one another. I won't pursue that in detail, but you can sort of see what I mean. Okay, so let me talk about how you form composites of state spaces. There's a reasonably obvious way to begin. If I think of A and B as test spaces controlled by two parties, let's say Alice and Bob, each of whom can perform the measurements corresponding to the tests in their respective test space, then I'd like Alice and Bob to be able to perform joint measurements, which would naturally be represented, or the outcome sense of which would naturally be represented by Cartesian products of the test in frac A and the test in frac B. If you gather together all the Cartesian products you can form this way, all the product tests, if you like, that gives you a new test space, which I'm using notation a little bit, I'll call Fraktur A cross Fraktur B. That's the space of product tests. Now, a state on A cross B is, I guess, what I would mean pretty generally by a bipartite state, or is one thing I mean by bipartite state, call that state non-signaling if it has well-defined marginal states. In other words, call omega non-signaling if the marginal probability of getting outcome X on the Alice side, calculated by summing over the probabilities in state omega of getting outcome X for Alice and outcome Y for Bob, over all of Bob's possible outcomes coming from test F, is independent of which test Bob has performed. So that Bob can't send information to Alice by means of the choice of which measurement he's making. And of course I want it to work on the other side too. Okay? So non-signaling states are those whose marginals are independent of the test made on the other side. That's what I mean by a non-signaling state. If you have two states, one for Alice, one for Bob, then there's a natural non-signaling state, a very simple one to define. It's the product state. Just multiply probabilities across the two systems. That is all obviously non-signaling. It's less obvious that it's influence-free because I haven't told you what that means. That's a typo. Influence-free is a term that we used to use for non-signaling. It's non-signaling. Okay, product states are obviously non-signaling. In general, for almost any test spaces you write down, there will exist entangled, that is, non-separable, non-mixtures of product states that are still non-signaling state, that will exist entangled states. Quite generic here. Now, there's a problem with this model. The problem with this model, form product tests and look at non-signaling states. Well, the problem is that in this model I can only form product tests. There's no entanglement between measurements. So we might want to fatten the model up. So here's what I might mean by a product in a more expansive sense of two test spaces. It would be some test space Fraktur C together with some embedding of this space of product tests in Frac C. So Frac C would in some sense contain the product tests. And I probably want to require some other conditions, such as first, that maybe states on the composite system are determined by their restrictions to product tests. That's actually kind of a powerful assumption. It would, for example, rule out real and quaternionic Hilbert space right off the bat. But maybe it's a plausible assumption. I certainly want to require that the restrictions of states on C to product tests would be non-signaling, and I probably want to require that every product state between A and B be a state on C. Okay? Condition 1 is probably less essential, but conditions 2 and 3 you'd almost certainly. Okay. That's it for my general survey of the framework I'm working in. I now want to restrict it. One of the features that really is characteristic of quantum theory is the degree to which it's very, very, very highly symmetric. Let's think about the space of orthonormal bases, or frames of the Hilbert space. If you give me two frames, think of them as the outcome sets of two quantum experiments, and you give me an arbitrary matching between those two sets, there is always a unitary, indeed a unique unitary, that implements that matching. That's symmetry of a very high order, right? A very strong kind of symmetry. And we can abstract it. Suppose you give me a group G. I'm going to say that a test space is a G test space if the test space comes equipped with an action by the group G on the total outcome set that carries tests to tests. Okay? So that the image of a test is still a test. Natural notion of an action on a test space. I'm going to say that a G test space is fully symmetric if under that action, well, first of all, this doesn't have to do with the action per se. If, first of all tests have the same cardinality, so it's a collection of outcome sets of a uniform size. And secondly, if the action of G on the test space has the property I just described for the quantum test space, namely that any bijection between two tests is implemented by an element of the group, right? So that if I have a test E 3 outcomes here, and test F with 3 outcomes here. This is almost invisible.
Yeah, that's totally right.
And I match any way I want these outcomes. I have to be able to find an element of the group, let's call it little g, whose action restricted to this test gives me exactly that matching. I'm not going to require at this point that that be unique. There are actually some interesting examples, even quantum mechanical examples, where it's not unique. Just think of the case where you're projectivizing everything. There are phase degrees of freedom. Okay, let me just stop for a brief moment. Is everybody reasonably comfortable at this point?
Except the chairman, who's worried that you're on slide 32.
It's not really slide 32. It counts as a separate slide everything with an additional bullet. There are 18 slides. I don't know which. Never a slide this is. Okay. One example we've already covered, the quantum test space of frames is fully symmetric under its unitary group. A more trivial example, take a classical test space. It's trivially fully symmetric, vacuously fully symmetric under its permutation, under the permutation group of its unique test. Now, it turns out that both of the exotic examples I showed, the grids and the test space of graphs of bijections, are fully symmetric. The former under the subgroup of permutations of E cross E, of the full array generated by row and column permutations, and transpose. And to be able to transpose rows to columns. The latter is actually fully symmetric just under products of row and column permutations. All right, now, it turns out that there is a recipe, and a pretty general recipe, for constructing fully symmetric test spaces. You can think of this as a kind of abstract quantization procedure, if you like. Begin with a single test, a single, so to say, classical test, something you're sure you can perform in the laboratory, a standard experiment. Designate one of these outcomes as a kind of base point, just for reference. It turns out which one you designate is more or less immaterial. Choose now an embedding of the group S of E, that's the symmetric group on E, the set of all permutations of E. Embed that permutation group in some larger group G, which maybe you think of as, at least conjecturally, the group of physical symmetries of the object that you're studying. Maybe you have some independent reason for thinking that the objects that you're considering have symmetries that aren't captured merely by permutations of the outcomes of your experiment. You think you know what it is, so hypothetically you want this embedded. You would certainly like permutations of your outcomes to be implementable by physical symmetries. Okay, now the rest of it is just sort of very standard stuff. You let K be any subgroup of this larger group that extends the stabilizer of your reference point in the symmetric group. So you just choose a subgroup of G that intersected with, sorry, this also is a typo, this should be S of E, intersected with S of E as embedded in G, gives you the stabilizer of your reference point. Now make a bigger outcome set, X, by just taking the quotient set. Just looking at the orbits of points in G under right action by K, or the left cosets of K. Condition 3 guarantees that you have a well-defined injection from E to X. If you just take any, again that should be S of E, take any permutation that sends x0 to any other point x in your basic set E, you can map x to the coset sigma k. It's well defined, that condition above, and also injective. This embedding. So X contains your original outcome set. And now do the obvious thing. If I can perform the experiment E and I think of each group element as a physical transformation, I should be able to transform and measure, or measure and then transform. So I get a whole bunch of additional tests just by looking at the orbit of this set E under the action of G. Call that fracture G of the basic set you started with. Okay? So, general recipe. You give me this embedding of the permutation group of E in a larger group, subject to this condition. I get a nice test space. It's easy to see that it's fully symmetric under G. And if I were to replace S of E in this construction by a possibly larger group H that acts on E as the full permutation group, I'd actually have a completely general recipe. Every fully symmetric test space can be built in this way if I have that little bit of extra freedom, which I'm not going to use for this talk, but it's nice to know that it's there. All right, we can construct finite dimensional quantum mechanics in this way. I'm not going to really bore you with the details, but the trick is let U of E be the unitary group on the obvious Hilbert space of complex functions on the set. Everything works in just the usual way, and you get the usual thing. Okay, question. Can we make this construction in some sort of uniform way so as to obtain not just a particular example, but a whole class of examples? Let's say a theory of suitably symmetric test spaces. Well, maybe. Here's how we probably want to proceed. We probably want to assign to every finite set, not just a particular finite set, a group G of A, every finite set A, a group G of A, and we want to have some sort of fixed embedding indexed by the finite set A of the symmetric group on A and some larger group G of A. We'd like that embedding to work in such a way that if we have a smaller set A containing a bigger set B, then the symmetries, this large symmetry group for A is embedded in a natural way in the larger symmetry group for B. And therefore, this also is a type that should be a capital B. If A is contained in B, it would make sense to take the intersection of G of A with the image of S of B inside G of B, and we'd like that to be just S of A again. Without going into too many details, what this suggests that we're after is a natural transformation from a functor, maybe the functor that assigns symmetric groups to sets, to some functor that, so to say, is larger, that assigns bigger groups to sets. There is an issue, though, of what functor is that the object part? Well, the symmetric group construction isn't really functorial in any easy way from, say, finite sets and mappings into groups. It is functorial between injections between finite sets and groups. So let's just look at the admittedly rather impoverished category, which I'm calling singe here, or singe 0, of finite sets and injected maps. Treat the symmetric group as a functor, or the object part of a functor, from singe to GURP. We'd like a natural transformation from that functor to maybe a larger functor, so to speak, G, from singe 0 to GURP. If you give me that much, if you give me that sort of natural transformation, and I have to be clear, I mean a natural transformation for which these things are still going to be true, then I can go through the recipe I showed you on the previous slide, in some sense simultaneously for every finite set A, and obtain therefore, for every finite set A, a fully G of A symmetric test space Fraktur G of A. And if I have that much, then I have at least a candidate for a product, for a unique or canonical product. Namely, if you give me Fraktur G of A and Fraktur G of B, so fully symmetric test spaces generated by taking A and B respectively as kind of canonical basic standard experiments, well, a joint system should have a joint measurement, A cross B. And then I generate the canonical fully G symmetric test space from that. So that's a candidate, the only reasonable candidate within this construction for a composite system. If we go through this construction in the case of the two exotic examples I showed you, grids and graphs of bijections, we find some interesting things happening. Certainly, there are sort of functorial extensions of the symmetric group functor that give us the grid test space for that. You let G of A be the subgroup that I described earlier, the subgroup of permutations on A cross A generated by transposition and row and column shifts. You embed the symmetric group in here by just looking at the first coordinate. Basically embed permutations, let's say row permutations. When you go through the recipe, you get back the grid test space, and therefore, of course, the tensor product that I've described would give you the set of rows and columns of the grid on A cross B. So that would be an A cross B by A cross B matrix whose rows and columns we're looking at. So That's nice in one way. It's not hard to show that that test space has arbitrary product states. That's good. Unfortunately, it lacks arbitrary product tests. Roughly because if you have a row times a row, or a column times a column, okay, that's okay. That's a row or a column in this sort of A cross B indexed array. But a row times a column is not. It's some sort of a block submatrix. It's not the right kind of thing to be a test. On the other hand, there is a little bit more good news, which is that states are typically non-signaling in this example. So it's got some good features, but it's also got a very bad feature. In particular, it's not a product in the sense I described earlier. Okay? Yeah. How much? I'm out of time. Okay. Can I prevail on you to give me, I don't know, 2 more minutes?
2 more minutes.
2 more minutes. Okay.
No time dilation.
No time dilation. Okay, I'll just go fast. Tails time dilation. If you look at the same recipe for a slightly simpler extension, let G of A be products of permutations, and use the diagonal embedding this time, then this recipe gives you back the test space of graphs of bijections, and you have a natural tensor product for that. And in this case, states at least do sort of restrict to non-signaling states. I do have all product measurements, so things are looking good, but unfortunately I can't form arbitrary product states in this example. So this has just the opposite set of good and bad features, apart from non-signaling, which good feature both have. Okay, I'm going to put the slides up but not read them. If I add 2 technical conditions, which I think are reasonable, one of which I'm calling regularity. Roughly, it says that that I can implement group symmetry operations by means of a kind of natural functor that you can get from the groups. Conditions satisfied by the unitary extension and the graph extension, but not the grid extension. Then I get a nice category. I can define, again, I won't read the details, I can define functors in a nice way associated with maps between not just the reference sets A and B, but any pair of tests in the 2 test spaces. And it composes naturally. So I have a category that I'll call G-test, G being the functor that I started with. Another condition that I need, which I also think is reasonable, with great imagination, I've decided to call reasonability. And it's simply that if I have 2 disjoint sets A and B, then the groups G of A and G of B, regarded as subgroups of the union of A and B, should commute pairwise. Roughly, if it's kind of like what Vernon was talking about. If I have these 2 separated systems, I know I've got one or the other. Well, if I perform a symmetry operation on one side or the other, it shouldn't matter which one I do. It turns out that if you have that reasonability condition, then the group associated with A fixes every point of the outcome space associated with a larger set minus A. That turns out to be a powerful property since it allows me to prove theorem 1. I'll skip most of this except to draw your attention to the last 2. If I have a reasonable extension, reasonable one of these functions, G, functors G, then this canonical product contains all the product tests. So the problem with the grids doesn't arise. And all the states are non-signaling when you restrict them to product states. If I enforce both of my desiderata, reasonableness and regularity, then not only is this true, but additionally, this sort of canonical tensor product is bifunctorial in product, and therefore is...
Unlike you, I'm not reasonable.
Okay, I know. Well, you like the last slide. And therefore is in fact a monoidal product on this category. Okay, there are lots of questions. Prakash doesn't want to give me time for any of them, but what does he know? So I'll just put them up one at a time. There are lots of questions.
I have a question period.
You can see them. The last one is perhaps the best. Okay, so I'm done.
Thank you.
Those are things.
Yes, and I'd like also to thank Mauro,
And
Steve,
That's fine, you can pass it.
We will